Hi, everyone. I thought it best to kind of evaluate where we're at. And actually, I'm very happy with where we are. So this was a part of the section on statistics that I had considered somewhat skipping over or glossing over. And in retrospect, I think that it would be to our great benefit to spend a little bit of time on this. So I'm going to spend a couple of lectures on data analysis and point estimation, just to familiarize ourselves with the way that one actually goes about collecting data and analyzing it and organizing it in such a way so as to present it to someone else and convince them of whatever it is that you're claiming in your data collection and analysis. So that's what this next couple of lectures is going to be. We have plenty of time to get to hypothesis testing and confidence intervals. Very, very pleased with where we're at. So if you'll just bear with me, I think that you will be greatly benefited in going through this material with me. I'm not going to assign really a lot of work on this part, okay? But at least be able to do and understand the problems that we do in the course of these slides. So I'll probably get through about half of these in this lecture, and then I'll get through the other half in the next one. Okay? All right, so let's look at this. Data analysis and point estimation. Okay, so first of all, there's this area of statistics. Now remember, when we talk about statistics, we're talking about taking samples from a population. Okay, and the area of descriptive statistics is just you're trying to describe the sample that you have gotten in some kind of meaningful way, right? And we're going to formalize that now. So sample has to be collected properly so that it is actually representative of the population that you claim it's coming from. Okay, so what would improper data collection look like? Well, here's an example I just wrote down. Cedarville wants to know how much exercise its students get in a week. So step monitors are given to 100 students. Okay. Now, in doing something like that could potentially, something called a confounding variable could really enter the discussion. Namely, students might be motivated to start exercising because you gave them those step monitors. So it wouldn't be an accurate reflection of the exercise that they would have gotten if they didn't know they were being studied. Okay? So you would have to set up your experiment in such a way that you didn't necessarily provide a motive for someone to start doing something they weren't doing at the get-go. So a simple random sample is just one where a subset of the population, any subset of the population of the given size that you're sampling has the same likelihood of being selected. Okay, so that would be the goal, is to get a truly random sample. There are several types of sampling that you can do. One of them is called stratified. That's where the data usually is somehow divided naturally into groups, which we call strata. Okay? And then we take samples from each one of those strata to make sure that we get something from those. Right? So an example that I have here is like maybe the strata are simply just men and women. So you have gender strata. But you might also have things like states, might be your strata, or countries, or maybe races, you know. You might have counties that might be your strata, and you want to make sure that you take sample points from each one of those. Okay, so something that you might do with your sample is compute something called the sample mean, which we started talking about last time with great vigor when we talked about the central limit theorem. Okay, so the sample mean, sometimes just called the mean, is denoted by x bar, and you have your data set of little n points from your sample, and you simply add those things together and divide by n. And if you use our fancy summation notation from calculus, that's how you would write that, right? So it would be x sub I, for I going from 1 to n, and dividing by n is the same as multiplying by 1 over n. All right. One drawback, so again, the sample mean, again, right now, if you look at the header of these slides, I'm talking about measures of center for your data. Like you're trying to find, okay, if I had to report one number that would be kind of like the describer of my data, maybe it would be the mean. So maybe that would be my measure of center, if you will. Okay, a drawback of using the mean is that it's really super sensitive to really big data values or really, really small data values. And that can cause the mean to shift around and be really subject to movement depending on whether I get a really big number in my sample or not. Okay. So look at this. If I have 1, 2, 1, and 2, okay, that's my sample. And of course, the mean is 1.5, right? That's easy to see, right? So the sample mean, you add those together and divide by 4, you get 1.5. Okay. But if I just change one of those numbers to a 10, okay, so it's like 1, 2, 1, and then I just change the fourth data value to a 10. Well, suddenly I have to go 14 divided by 4, which is 3.5. That massively changed the sample mean, just changing that 1 point. And in some sense, you kind of say, oh man, I don't know that that's good, that I can just change one data value like that and it just jerks the whole mean into the stratosphere like that. So the mean as a measure of center is sometimes frowned upon. I mean, you still kind of report it. It's such a standard statistic that you get from a sample, but the sample mean is sometimes it's so prone to fluctuation depending on your sample. I'm only talking about sample means right here, not the population mean. The population mean is the population mean. That doesn't change, right? The population mean is the population mean. It is a constant, it does not change. We don't worry about outliers because that takes into account everything. But the sample mean is a random variable. And as such, if you happen in your sample to get a really big number, it'll kind of jack that thing up. Okay, so that's a little bit disturbing to us at times. All right, so here's another potential candidate for a measure of center. It's called the sample median. And what I mean by that it's robust to outliers is that it's not prone to being jacked around by really big or really small numbers. Okay. How do you get the sample median? Well, it's obtained by first ordering your n observations, smallest to largest. Any repeated values are also included. X tilde is the sample median. Okay. And it's the middle value if you have an odd number of data points. And it's the average of the two middle values if you have an even number of data points, because there you're going to have two things that are in the middle. You have like 6 data points, then the third and the fourth are the ones that are in the middle. And you would take their average. That would be the median. Okay. So let's see here. Here's a little problem. Okay. Given the following observations in pounds per square inch, determine the values of the sample mean and the sample median. Okay, the sample mean and the sample median. Look, I'm not going to go through the computation for the mean because it's fairly easy. You know what I'm saying? You just add them together. You have a total of 8 of them, and you divide by 8. Okay, so that's a fairly simple computation. But now, what about the sample median? Well, I have to order these things. So let me just order. Okay, so first of all, 8 is number 1. Okay, so 8 is number 1. What's number 2? Well, 8.9. What's number 3? Well, 11. What's number 4? Well, 12. What's number 5? Well, 13 is. Okay, and this is number 6, 7, and 8 by rank. Okay, so how would I find the median of these 8 data values? Well, I would take the 4th and the 5th, okay, which are 13, and 12, and I would compute, I would get that X tilde, which is the median, is the average of those two, which is 12 and a half. Okay? There it is. And it says, by how much could the smallest sample observation be increased without affecting the value of the sample median? Well, here's the smallest value. And I could actually bump this up. I could increase this by 4. I could really kind of crank this thing up and not affect the sample median. The sample median would still be the same. But the minute I get beyond 4, I start affecting things. Okay. And by the way, I could drop that first value by any amount. I mean, I could change that 8 to like, negative 30,000, and the sample median would still be 12 and a half. So the sample median is not getting jacked around by huge fluctuations in other values. On the other hand, the sample mean would get hugely jacked around by those. Okay. So it's interesting to think about. Okay, now, so those were a couple of measures of center that I wanted to kind of put into your cognition. Specifically, the sample mean and the sample median. And just know that the sample mean is prone to being jacked around by outliers. Not the population mean, sample means. So that's a random variable depending on the sample. But the sample median does not get jacked around by outliers. Okay. Now I want to talk about data spread, like how spread out the data is. And there are several ways to describe the spread of the data. We've already talked about variance, and we're going to have something that is basically trying to capture variance for us here pretty soon. But one kind of obvious thing to do is you just take the range, which is the largest observation by the smallest observation. That's one very basic measure of variability, okay? But you also have the so-called sample variance. Now notice sample variance, I use S squared, right? So population variance, right? So population variance, that was like sigma squared. And so the population parameters get little Greek letters, right? So sigma squared is the population variance, mu is the population mean, x bar is the sample mean, and S squared is the sample variance. Okay, how do we compute it? Well, okay, so remember, like for variance, we're always comparing each data value. We were comparing each data value in the population against the mean and seeing how, we were seeing how far apart those were. We were squaring those, and then we were multiplying by the probability that that data value happened. That's how you got the variance. Since I don't know anything about the underlying distribution for a sample though, I mean, after all, that's the whole reason I took the sample. I don't know what's going on with the population. I don't know what the probability of any one of those data values is. So what do? I can't quite multiply, right? I can't go in here and take each data value minus, so first of all, I subtract X bar because I don't know what mean is, right? So we don't know. We of course don't know the population mean. So we use X bar. We take each of our data values in our sample. We look at how far away it is from the sample mean. We square that difference so that it ends up being positive. But then it's like before I would put like the probability of xi in here, but I don't know what that is. So what do? We instead just kind of multiply each data value. I factored this out, but we multiply each data value by 1 over n minus 1. Now this little minus 1 right here might be a little bit perplexing to you. It's like, what in the world is that? Is it n minus 1 for? Why not just 1 over n? Well, the reason is if we do 1 over n, you tend to underestimate. Remember, this is supposed to be an estimate for the population variance, okay, which we don't know. It's supposed to be a good estimate for it. Well, in general, when you take a sample, you tend to not get the things that drive up the variance because those are rare, okay? They're like outliers. Okay, so you tend not to get those. So you tend to underestimate the variance if you just take 1 over n times these squared differences. So to bump that up a little bit, it turns out you can theoretically prove that the best thing to do is, instead of multiplying everything by 1 over n, which is basically dividing all of the sum of these squared differences by n, you divide by n minus 1, and that drives up the sample variance a little bit. And by the way, if you go through, let me just clear this out because that's looking messy. If you kind of go through and square everything out, you end up getting this little formula right here, okay? Which is generally a little bit easier to compute. All you do is you add up the squares of the data values, and you subtract off the square of the sum of the data values divided by n, and you divide everything by n minus 1. Okay, the sample standard deviation, of course, is just take the square root of s squared, right? Why not? You know, the same sort of thing. Remember, so like for the population standard deviation, that's what you did with the variance, square root. Do the same thing here. Okay, this is a representative value of the deviation from the mean in the sample. Okay, right. So here we're kind of trying to capture what's potentially going on in the population by extracting similar information from the sample. Okay, so this is the sample variance and the sample standard deviation, which measures how far the data values, I mean, look at it. You're measuring how far each data value is from the sample mean. Squaring those so that you're kind of getting a measure of how far the data is tending to deviate away from the mean, and then you divide by n minus 1 so that you don't underestimate the population variance. Okay? But these are estimates after all. Remember I told you, statistics, it's all estimation. Doing estimation, we're doing a kind of best guess. It's kind of a dirty science. It's not like, you know, we don't have as much certitude as we did in the case of probabilistic stuff, where we knew everything about the underlying distribution. Okay. So here's just a little fact that we can take to the bank. So if I have a sample of n points and c is any non-zero constant, okay, so it's just any non-zero constant. Suppose that s sub x squared is just the sample variance of the xi's. I'm putting an x there to remind you that that's just the original sample variance from those x's. And then what I'm going to do is I'm going to take all the I'm going to take all the x's and add c to everything. I'm going to add c to everything. Well, what do you think that's going to do to the sample variance, right? If I create this new sample by just adding c to everything, do you think that's going to change the variability? Well, no, you've just shifted everything by c. Okay, so the variability is going to be the same. So it's not surprising that actually, if you go and you do the math, the sample variance is exactly the same for those new data values, where I've added c to everything. It's exact same as it was for the original data. Okay, and what about this? Okay, so in the second case, what happens if instead of just adding c, I multiply everything by c? Well, not surprisingly, because remember in the formula back here, okay, in the formula back here, look, everything was squared, right? So if I multiply everything by c, I'm going to get a c squared that kind of factors out of everything. So it's not too surprising that over here I see, okay, if I scale all the x's by c, right? So scale by c, right? Scale everything by c. Then what happens? There's going to be a c squared that factors out of that formula, and it's just going to be c squared times the original sample variance. And so the sample variance for those scaled things is c squared times the original thing. So adding c doesn't change anything because it just shifts everything by c. But scaling everything by c does change things by a factor of c squared. Of course, if you take the square root, you need to make sure you take the absolute value of c, because c could have been negative. So that's the relationship between those things. Okay, moving on. Given the following observations, calculate the deviations from the mean Okay, right. So calculate the deviations from the mean, and also using the answer to, so deviations from the mean, that just means you you compute the mean, and then you take each data value and you take the difference between them, and then we're going to square things so that we can compute the sample variance and sample standard deviation. Okay. And this part right here, part C, that says use the second formula given in the notes. That's this one right here. Okay. That formula right there. Which actually avoids, I mean, the thing is, I can use that formula without actually computing X bar. Isn't that kind of interesting? Okay. Looks like I basically kind of avoid computing X bar when I do that. That's interesting stuff for sure. Okay. I don't know if I'm going to do that part of the problem, but I'll do the other things. Okay. So we'll take this data and we'll actually go and work it out in Excel. Okay, so I'll be right back with you. All right, we are over in Excel. Copied the data over. All right, and my goal is to compute the. My goal is to. I'm gonna move this thing over here. My goal is to compute the sample variance. Okay. So let's see here. Let me move this up here. Okay. And I want to have a column here for the squared diffs, squared differences. Okay, so this is my data right here. I'm just labeling things nicely. Squared differences. Okay, so first of all, I want to compute X bar. There's a couple of ways I can do that. I can either go equals sum, and I can actually add these up myself. And how am I doing this? Well, I selected the first thing. I can either grab the corner and drag it down over the data that I want, or I can, once I click the first thing, I can hold down Shift. Oops, oh man, what did I do here? Okay, I can click the first thing like this, and I can hold down Shift and hit the down arrow and grab my data. Okay, and I want to divide this thing by 5. I get that. But there's another way I could have done it. I could have just said equals. There's no mean function. So if I try to type mean, it's not in there. There is a median, but there's no mean function. Okay. But if you type average, that's the mean of the sample mean. Okay, so let's see. This. Okay, so these things, hit enter, and of course it's the exact same thing. I'm just trying to show you that. What about squared differences? Well, so I go equals. Okay, so parentheses, this, remember it's X value minus X bar. Okay, and here's the thing. So if I go like this, hit enter, I get, oops, I forgot to square it, right? So I also need to go raise to the power 2, okay? That's squared difference, okay? So I get that. Now here's the thing though. In Excel, you can drag formulas down. So if I grab the lower right corner of this and drag it down, it's going to give me this, but I start saying to myself, what on earth is going on? These numbers got massive. Well, that's because when you grab and drag down, it's going to advance down the column automatically. And you didn't want it to do that. You wanted it to keep just 115.58 where it was. The way you can tell it to do that is you can put a $sign in front of the rows and column numbers that you want not to get shifted automatically when you drag the formula. Okay, so I put $signs on C2 because C2 is the sample mean, and I don't want that to advance. Okay. So I hit enter and I get that, and watch. Now this will change if I drag this formula down. Okay. I get that. And so that's the squared differences. Okay, so let me kind of insert a column here. and I'll do sum of square diffs right here, sum of the squared differences. Okay, so this is going to be equal to the sum of these. Okay, and actually, at this point, I really don't need to do much else. I'm just going to go, I'm going to divide the sum of the squared diffs, and I'm going to divide this by n minus 1. So it's 5 minus 1. Okay, like that. So let me just say this, let me write this here. This is what s squared is. S squared equals sum of squared diffs divided by n minus 1. Okay, total number of things minus 1. Okay, and I get 0.482. Now, there actually is a formula rendering of this as well. I could go, you know, s squared, what is it? I go equals, let's see, if I want variance, look, there's variance for a sample, which is var.s. And then it asks me for the data, which is right here. And in theory, I should get the exact same thing as what I just got. 0.482, it's exactly right. See that? So that is CUM14. I'm not going to go through the application of the other formula where I don't have to find X bar. I'll kind of leave that up to you. But that other formula is kind of nice because I don't have to go through the actual finding of X bar itself. Okay? All right. Okay. Here we are again. So we computed the sample variance. It says if the value 100 is subtracted from each observation, how will S squared change? Well, it won't, because this is a measure of variability. If everything gets shifted by 100, same variability. Okay, that's not going to change at all. If you go through the computation, the sample mean will shift by 100, but so will every data value. So when I compute the difference between those two, the minus 100 will just cancel from each one of those summands in the sum of the squared differences. Okay, so it won't change. What if each observation is multiplied by 100? Well, if each observation is multiplied by 100, remember, that will multiply the sample variance by 100 squared. Okay, that's what we had in the last slide. Right here. Right, oops. Right here. Okay, so just to kind of remind you of that, right? It will multiply the result by 100 squared. Okay, so it will massively change that thing. Right? And I want to talk a little bit about organizing data, and one way in which we can do that effectively is with something called a histogram. In all likelihood, you probably already know what this is. I just want to go through it in full rigor so that we're ready to use it at will later on. Okay, so the frequency of any data value is the number of times that the value occurs in a data set. Okay, so you know, you might have a whole bunch of 5s or something like that, and the number of times a 5 appears is called the frequency of that data value. Okay, the relative frequency is the percentage of time that that particular value is happening. So how would you get that? Well, you would just take the frequency and divide it by the total number of data values. So that's what that formula is. A frequency distribution is just a table of frequencies or relative frequencies, right? So you could just talk about the actual numbers themselves, the frequencies themselves, or you could do the actual relative frequencies if you want to talk about percentages for those data values as opposed to the numbers themselves. So let's talk about constructing a histogram for discrete data first. Okay, so it's more advisable to use for discrete data to use the relative frequencies as the kind of vertical height of these things, and then to, like, for each particular discrete data value to kind of use that as what's labeling that particular rectangle. And you make a width of 1 so that the area of the rectangle is actually equal to the probability of each one of those data values. That way you'll have the area of various rectangles simply being the probabilities that those data values occur. Okay? So to construct a histogram for continuous data, you have to decide, okay, how wide, because you can't talk about individual data values anymore for continuous data because the probability of any individual data value is 0. So what you do is you make like interval widths, okay? And the widths of those intervals, you're going to count the number of things that fall into those intervals, and that will make your frequency. Okay, so now frequency becomes about how many data values fell into our particular interval of values. Okay, and the width of each one of those is called a class width. Okay, so you have classes, and you count the number of data values that fall into each one of those classes, and that forms your height. Either you count the total number of things that fell in there, that would be a frequency distribution, or you count the percentage of data that fell in there, that would be a relative frequency distribution or histogram. Okay, so you make class boundaries on the horizontal measurement. So like you might go from 0 to just 0 to 1, not including 1, and 1 to 2, not including 2, etc. Rectangle height is the relative frequency of each class. A basic rule of thumb when you're trying to decide how wide you should make your classes is you may mainly like look at the upper and lower numbers, and you want to have class widths that are wide enough so that you have basically the square root of n total classes. Okay, total classes. So so for instance, if your data goes all the way up to from like 0 to 100, then you would want to have a square root of 100 classes, which is 10. You want to have 10 classes. And so, maybe your class width there should just be 10, 10, 10, 10, 10 going all the way up. Okay, and you'd have a total of 10 classes. That's not really a strict rule of thumb. It's just, if you only make one huge class, it's not going to be very helpful because you're going to have 100% of the data in there and you're not going to have any idea like how this data is distributed. But square root of n classes breaks it down enough that you can start to see the shape of the distribution, okay, how this data is behaving. Okay, so here's a relative frequency histogram. The percentages of data that fall into certain ranges are right there. You can kind of tell that the class width here is about 10 or something just by looking at the x-axis. Okay, the first class goes from 170 to 180. Looks like you have just under 2% of the data falling in that range. From 180 to 190 is the second class. And it looks like, about 5% of the data falls there, et cetera. So if you added up all those y values for each one of those classes, you should get 100%, right? You should get 100%. Yeah. So let's talk about constructing a histogram for continuous data using unequal class widths. Sometimes, unequal class widths are good when some regions have a much higher concentration. You have like tons of data in one area and not that much in another. Maybe you want to refine the place that has tons of data in it a little bit more so that you can get a better idea of what's happening. So use smaller class widths in areas of high concentration just to refine it more. Larger class widths in areas of low concentration. Rectangle height is now, relative frequency divided by class width. Okay. Rectangle heights are called densities, and the vertical scale is the density scale. The reason you use this weird rectangle height is so that the area still corresponds to probability. Okay, I'm not going to go really into this, but you always want the area, that you add up under the rectangular heights to represent probability. Okay, so to make that happen, that's why you do this weird formula for the rectangle height, relative frequency divided by class width. Rectangle heights are called densities, and the vertical scale is the density scale. Okay. So this is an example of when you might use unequal class widths. Okay, you didn't have You had a lot more data on the lower end, so you kind of refine that a little bit more, and you have class widths that aren't quite as wide. Whereas on the upper end, you weren't encountering as much data, so you made wider class widths. That gives you an idea of what the shape of the distribution is. Given the following frequency distribution, construct a histogram. Okay, so what would a histogram look like in this case? So a frequency distribution, construct a histogram. Well, the frequency distribution, would look something like, so here's this. So 0 to 2. Okay, so maybe, 2 goes right here, and then 2 to 4. Okay, and then what does it say? 4 to 11. Okay, and then what? 11 to 20. Okay. Okay, 20 to 30, and then 30 to 40. I'm just kind of roughing this thing a little bit. Okay. Now what do? We have 136 in this first thing, right? So, 136. I'm actually just, right now I'm just doing the frequency, the frequency, right? So this is 136. What about between 2 and 4? It's like 92. Okay. So sometimes you'll write these numbers on top of them. 92. From 4 to 11, I have 71. Okay. From 11 to 20, there's 26. From 20 to 30, there's 7. From 30 to 40, there's 3. Okay, and again, I'm being very, very rough here. Again, if you wanted to have, this is a frequency histogram. Relative frequency, remember you'd have to do that weird formula for the rectangle height, but all that would do is like, the shape of this would look exactly the same. It would just change what the Y value actually was. But it would look exactly the same, exact same shape. Okay, and I'm not wanting to spend tons of time on this. You could spend a ton of time on this. Okay, and actually Excel has the ability to make these histograms automatically, but you really have to strong arm Excel into doing what you want with class widths and whatnot. It's a little bit annoying actually. It's almost easier to make them by hand in some ways. Okay, let me clear this out. Okay, so some terminology to end on here. Unimodal histogram is something that has this general shape right here. It just has one thing in the middle. And by the way, the word mode is the most frequently occurring data value. That's also a measure of center that we didn't talk about. And you could have multiple modes if there are multiple values that occur very frequently. So unimodal means there's a single peak. Okay. Bimodal is a place that you have a couple of different peaks. Okay. This happens in practice a lot of times when you have two kinds of individuals or various heights of 22-year-olds in the US and 5-year-olds in the US. Okay. Number of peaks can depend on how the histogram is constructed. Again, if you kind of tweak some of the class widths and lump some of the data together, it could cause the bimodality to disappear in some cases and make it more unimodal. So you have to kind of use discernment when you're doing that. Multimodal has more than 2 peaks, and a histogram is symmetric if the left half is a mirror of the right half. If you have a symmetric, sometimes you say it's mound-shaped, that means that you start to suspect the thing is normal, and that to invoke the central limit theorem, when you kind of graph the data and you see that it's symmetrical, you're going to have the ability to invoke the central limit theorem with very little data, not necessarily the 30 or more rule that we had certainty with. Okay. A positive skew is where you have to be careful. A positive skew means that you have values that are, there's a tail that's to the right of your data that tend to drag the mean up. Okay, so these things up here on the top end are causing the positive skew, and it's going to like drag the mean or the mean for your data upward. Okay? A negative skew has a tail on the left like this. Okay? So it's negative skew and positive skew. Okay, and there are plenty of distributional situations you can find yourself in where this sort of thing happens. The exponential distributions are positively skewed, right? Those kind of exponentially decay. And so you see this long tail off to the right, and there's not even a tail at all on the left. It's a positive skewed distribution, okay? And how, what gives me the right to declare when it is that I think the data is bell-shaped, or that basically the data comes from a normal distribution? Well, one empirical rule is one that we've kind of already talked about, namely, if I go to the sample mean and I go up and down by the sample standard deviation, if I encounter roughly 68% of the data, and that's exactly what happens in the case of the normal distribution. If I encounter 68% of the data, and then if I go out 2 standard deviations from the sample mean, I get 95%. And if I go out 3 standard deviations, I end up with almost all the data, namely 99.7. Then I strongly suspect I'm dealing with a bell-shaped distribution and that the underlying population probably is approximately normal from the get-go. And so invoking the central limit theorem is going to be possible with a very small sample size. Okay, I'm actually going to leave it at that. And next time, which will be Monday, because Good Friday is a holiday, I will talk about exploratory data, and we'll finish this material off. Okay, that's all for now. Have a good weekend.